Overhead bins are rattling, the wings are flexing, your drink just hit the ceiling, and the pilots are doing absolutely nothing because they don't need to. Here's why. Just after takeoff or in the final moments before landing, the first bumps often come from the ground itself. Wind rushing over hills, forests, or city skylines gets chopped up by surface friction, spinning off invisible eddies. Some are as small as a car, others stretch hundreds of meters across. These swirling pockets of air, called mechanical turbulence, form in the lowest few thousand feet of the atmosphere, right where planes are climbing or descending. That sudden side-to-side jolt as the wheels leave the runway, or the shudder as the plane settles toward touchdown, comes from this churning layer. Now add in a summer thunderstorm. When sunlight heats the ground, pockets of warm air break free and rise, sometimes punching all the way up to the cruising levels as powerful updrafts. Inside a storm cell, the energy, convective available potential energy, and commonly called CAPE, can top 2,000 joules per kilogram. That is enough to launch columns of air upward at highway speeds, tossing an aircraft in all directions for a few seconds. Pilots avoid the heart of these storm towers, but even passing nearby can send a sharp bounce through the cabin. These low to mid-level bumps are physical, visible, and familiar. They are different from the invisible high-altitude jolts that catch everyone off guard at cruising speed. But for most passengers, the sensation is the same, a sudden, stomach-dropping reminder that the sky is alive with motion. At cruising altitude, the sky can seem perfectly calm, but clear air turbulence, called CAT, waits unseen. The jet stream, a swift river of air high above, is the usual suspect. Where it brushes against slower air, a sharp boundary forms, sometimes just 200 to 800 meters thick. Across this narrow band, wind speed can jump by more than 25 meters per second per kilometer. Here, the air splits into layers, sliding past each other like sheets of glass. When the speed difference is steep and the Richardson number drops below 0.25, the air turns unstable. Invisible Kelvin-Helmholtz waves ripple through, impossible to see or detect on radar. Aircraft crossing this zone can be jolted without warning, vertically or sideways, sudden and severe. Pilots know this as the most unpredictable turbulence, striking without visual clues. The jet stream obeys only physics, indifferent to comfort or flight plans, shaping a threat engineers must always consider. Aircraft wings are engineered to flex, not snap, under pressure. Certification rules require every jet to endure at least plus 2.5 G and minus 1 G, with a safety factor of 1.5 built in. That means a Boeing 777's wing can bend nearly 26 feet at the tip before any permanent change occurs. In static test footage, the wing rises in a smooth arc, holding loads far beyond what turbulence delivers. Most in-flight gusts register between 0.5 and 1.5 G, well within the design envelope. Even the rare 2.9 G spike recorded on a 777 falls short of the ultimate limit. Composite wings, like those on the 787 and the A350, take this further. Carbon fiber layers distribute stress, absorbing energy and reducing the risk of a single-point failure. Destructive tests confirm this. Composite wings withstand repeated flexing and only fail after surpassing all expected loads. The numbers reveal a structure built to handle the sky's worst with quiet assurance. Inside the cockpit, the response to turbulence follows a practiced rhythm. The crew scans weather radar for storm cells and wind shear, adjusting the tilt and gain to catch even faint echoes. They cross-check these radar sweeps with pilot reports streaming in over data link, building a mental map of rough air ahead. Air traffic control joins the loop, relaying turbulence advisories, and when needed, clearing altitude changes to sidestep the worst layers. If a shear zone looms, the captain requests a climb or descent, sometimes just 1,000 feet, to slip above or below the disturbance. Speed becomes a shield. Pilots dial back to VA, the turbulence penetration speed, calculated to keep the airframe within its certified plus 2.5 G limit, even in a sharp updraft. The autopilot takes a lead role here, its gust-damping algorithms making rapid, precise adjustments to pitch and roll, often faster and smoother than any human hand. Flight management systems flag high-risk airspace on the navigation display, suggesting alternate routes or altitudes. Each step, from radar scan to pilot reports, air traffic control coordination, speed reduction, and autopilot damping, forms a layered defense. The goal is simple: keep the aircraft inside its structural envelope, keep passengers buckled, and turn what feels like chaos into routine. For the flight crew, these are not emergency maneuvers, but standard operating procedure, calm, methodical, and proven. Singapore Airlines, SQ321, and United Airlines, 826, both faced sudden, violent, clear air turbulence at cruising altitude. The aircraft structure held firm, no cracks, no loss of control. But inside the cabin, the story was different. On SQ321, one passenger died and dozens were hurt. On UA826, there was another fatality and a cluster of injuries. The pattern was unmistakable. Nearly every serious injury involved someone who was unbuckled at the moment of impact or cabin crew caught standing in the aisle. Official reports from investigators found that seatbelt compliance, not airframe failure, was the deciding factor in who walked away unharmed. In 30 years, fewer than 5 turbulence-related fatalities have been recorded worldwide, all linked to human behavior, not structural collapse. The seatbelt remains the single most effective defense against the chaos of rough air. Climate researchers now warn that moderate to severe clear air turbulence could jump by 40 to 170% by 2050, as shifting jet streams carve sharper boundaries in the upper atmosphere. But while the threat grows on paper, the body's reaction tells a different story. The inner ear loses its horizon in a sealed cabin, so even a gentle jolt can trip the brain's alarm, especially when a creak or rattle sounds nearby. Modern technology, like satellite turbulence mapping and automated detection, gives pilots more warning than ever. But the real challenge is that our senses are tuned for solid ground, not the invisible waves of the skiing. Your body screams danger, but the data says otherwise. Fewer than 5 fatalities in 30 years. Aircraft are engineered far beyond what turbulence delivers. The real risk? Ignoring your seatbelt.